What's up, guys? It's me, Sir Ernest, and today we're going to talk about the linear momentum of a system of particles. So if we have a system of particles like this, okay, the system of particles have separate or have their respective masses as well as their velocities. For example, this particle is moving in this direction. So in this case, this is m1. So this will be v1. This particle is moving in this direction. So this is v2. So this is m2. Okay, so for example, this is the representative the velocity of particle n. Let's say this is particle I, so this is representative particle mi, and let's say the velocity is vi. Okay, so all these velocities are measured with respect to a certain coordinate system. So the linear momentum of the system of particles is given by the vector sum of the linear momentum of the individual particles, where I is equal to 1 to n. By definition of linear momentum, this is equal to the sum of mi times vi for all I, where I is equal to 1 to n. Okay. On the other hand, the velocity, for example, of the center of mass, say this would be the velocity of the center of mass, bcm, is actually the time derivative of the center of mass, position of the center of mass. Okay, so this is now equal to the time derivative of sum of mi ri divided by capital M, where I is equal to 1 to n. Because mi and capital M does not change with time, so this is actually equal to the sum of mi times ri dot for all I divided by the total mass, or sum for all I of mi vi divided by capital M. So this is now the velocity of the center of mass. Now this suggests that, okay, so we're going to look at this numerator is actually equal to the total momentum of the system. So therefore, the total momentum of the system of particles is actually equal to the total mass of the system times the velocity of the system. So in other words, if you know how the center of mass moves, and you know the total mass of the system, you can directly compare or compute for the momentum or the linear momentum of the system. You don't have to know the individual masses as well as the individual velocities of the individual particles of the system of particles. Okay, so in other words, the linear momentum of a system of particles is just equal to the velocity of the center of mass times the total mass of the system. So here we can see that there is some kind of a collective behavior among the system of particles. Now let's say that there is a force on an external force that acts on each individual particle. So for example, this representative particle mi, there is an external force Fi. So again, this is external force. Okay, so let Fi be the force on particle I in a system of particles that is applied externally. So also there are forces in between these particles. So for example, this particle I is exerting a force on particle F. Particle, let's call this particle J. And this particle J exerts a force on particle I. So let's say this is the force exerted by on I by J. So this is applied internally. So therefore, the net force on the particle I will be equal to the force applied externally plus the sum of all the forces acting on I by the other particles J, where J is equal to 1 to N. Newton's law tells us that this is equal to the mass of particle I times the acceleration of particle I, which is equal to the time derivative of the linear momentum of the system. Okay, so therefore, the net force on the system will just be the sum of this. So this is sum of Fi for all I plus the sum of Fij for all I and for all j. And this is equal to the sum of the total linear momentum time derivative for all I, for I is equal to 1 to N. Now, here it is understood that this particle is different from this particle. So that means I can never be equal to J. Because remember, the particle cannot exert force on each other, on itself. So Fii will be equal to 0. So by Newton's third law, this tells us also that Fij will be equal to negative Fji. So therefore, this term sum, so this is a double sum for all I and for all j, Fij should be equal to 0. Because if you're going to, let's say, set I equal to 1 to 2 and j equal to 1 to 2, you'll end up with 0. Okay, so this is 0. So therefore, the sum of Fi for all I will be equal to this term, which is equal to sum of the time derivative of mi vi for all I again, or time derivative of the sum of mi vi for all I. And we know that this is equal to this one. So therefore, the sum for all Fi is equal to the time derivative of capital M times V Cm, which is equal to mass times the acceleration of the center of mass. So where ACM is the acceleration of the center of mass. So this equation tells us that the acceleration of the center of mass of a system of particles is the same as that of a single particle having a mass equal to the total mass of the system and acted on by the sum of internal forces. Okay, so that's why when, for example, what we usually do when we have, let's say, an extended object like a box, this is actually we usually draw this as follows, no? So let's say there is a external force acting on this box. So what is actually implied here is that this external force is actually applied on the center or on the center of mass of this box. So this center is actually the center of mass of this box, and this force is actually applied on the center of mass, and the center of mass is represented by the total mass, capital M, and this ACM is actually the acceleration of this system of particles. Okay, so for example, let's say for example there are no external forces on the system, so this means this is 0. So that means the time derivative of mvcm, which is the momentum of the system, is equal to 0. So therefore P is equal to a constant. Okay, so this is called the conservation of linear momentum. Okay, so that's it. That's the linear momentum in the context of a system of particles. In the next video, we're going to extend our discussion to angular momentum of a system of particles. But for now, thank you guys for watching. I hope you learned something today, and I'll see you guys in the next video. Bye-bye.